Hello. Last time we had seen the basic formulae for integration. These are a few of them, 5 of them that I have listed here, but of course there are some more. We had learned that this integration works. Okay, works only when over here you are having x. Okay, for example, what I'm trying to say is, if in place of x you have something else, for example, you have sine x, okay, power n. In place of x, suppose you have sine x power n dx. Then you cannot use this formula anymore. You cannot simply replace x by sine x power n plus 1 divided by n plus 1 plus c. Okay, so this formula won't work anymore. You cannot do the problem like this. So this is exactly what we will learn today. How to do such problems if other terms are involved. Okay, for example, even over here you may have 1 by tan x, or you may have 1 by 2x squared plus 1. Okay, suppose you are having something like this, 1 by 2x squared plus 1 dx. You cannot use this formula anymore. Okay, because this formula works only when you have a single variable x. Okay, it doesn't work when x is replaced by something else. Okay, so when we encounter such cases, that is when we will have to use substitution, or we will have to change the variable from x, we will have to change into another variable. However, this basic formula works if in place of x we replace by t. Okay, because x was chosen just for notation. Even if we have t power n, it still has this form, okay, dt, then you can still use this formula, t power n plus 1 by n plus 1 plus c. We can still use this formula because we have done nothing. It's just that instead of x we are writing t. Similarly for this one, even if we are having z, suppose instead of x we are having z, 1 by z, but over here also we have changed it into dz, then this formula still works. Okay, we can still do it like this. Similarly, if we replace it with another variable, this forms the basis of what I am going to discuss today. That is, let me repeat again, the substitution or the change of variable. The basic rule that we will follow over here when substituting or changing the variable is that we will substitute terms so that the integral becomes easier looking. Okay, it looks better. Okay, for example, you may have a very complicated looking integral, but we will try to substitute some terms in that integral so that the integral becomes better looking. All right. Okay, let me just illustrate with an example. Okay, I will use this book. Okay, suppose, okay, this is the first example on substitution. Ex squared dx. Okay, so sorry, it is e power x cubed dx. Okay, so this integral, it is looking very complicated. Okay, it no longer falls into the basic formulae that we had seen. But what we will do, we will substitute some terms to make it look a bit easier. Okay, this is looking too complicated. So what we will do, okay, we know that in the formula, we had only a formula for e power x, right? Integral e power x, we do have this formula. Okay, so maybe it gives us a bit of an idea that we will have to substitute this one by another variable. Okay, we will substitute x cubed by another variable. So the solution starts like this. The substitution, we will always write it maybe to the right hand side. It's not a rule, okay, but it's best if we keep the main solution over here. Any kind of rough work, okay, we'll do it on the right hand side. Okay, so we will substitute x cubed by another variable. Okay, some of you, you can write this one by t, you can write it by z, whatever way you like. Okay, but I'm used to writing it as z. Okay, so I will write it as z. So what will we do now? Remember that when you are having xx, okay, similarly over here you are having dx, but when you have changed the variable to z, then this dx will also have to be changed into dz. Okay, or if you change it into t, then dx will also be changed into dt. Okay, how exactly do we do that? Is by differentiation. Okay, all right, so you notice over here, if we differentiate both sides with respect to x, okay, you will get something like this. Okay, so ddx of x cubed is 3x squared, and over here we will be having dz dx. Okay, we cannot do anything with this, we have to leave it as it is. So what we will do, okay, so we will be getting 3x squared dx equal dz. Okay, but over here you notice that x squared dx, there is this term x squared dx also. So what I will do, I will write this one, x squared dx, divide the whole thing by 3. So you'll be getting dz by 3. So the solution, okay, I will denote this one first by I, it will be equal to integral. Now you notice that x squared dx has been changed into dz by 3. I will write it to the end. Okay, dz by 3. Okay, so x squared dx has been used. Now all that is left is e power x cubed. E power x cubed will be e power z. Okay, this is 3. So now you see that this integral, it's looking easier compared to this. Actually, we can even take the constant outside now. So you will be having e power z dz. Now this formula, it is a basic formula that we had learned. We can use the basic formula for this integral. You will be getting e power z plus c. Okay, so over here, but the original problem was stated in terms of x, but we had got a solution in terms of z. So what we will do next is we will change this z again into x. Z is equal to x cubed. So this will be the answer. Okay, so the main point over here is this: when you are having x everywhere, even over here you will be having dx. When you are having z everywhere, ultimately you will have to change it in this one also into dz. Okay, do not ever try to integrate something like this for now. Okay, when you are having x squared and dz, okay, just know that there is some mistake in your calculation. Okay, so this is the first example, the solution of the first example. Okay, now let us see another problem. Okay, integration 1 by root x sine root x dx. Okay, so this is the second example. We have to integrate this one. Again, we are having a formula only for sine x, right? But over here we are having root x. So the formula no longer works, and also we are having this term over here, right? It's looking even more complicated. So what we will do, I will try to substitute this one. Let root x equal z. After writing this one, you know immediately that we will have to differentiate. Differentiating both sides with respect to x, dz dx. Differentiation of root x will give you 1 by 2 root x. Okay, and you can carry this one over here as well. So you'll be getting dx equal dz. Okay, but again, if you take a look at this problem, you are having only 1 by root x, you can combine it with dx. So over here we will take this to that side. So the integral becomes, combine this one and this, you will be having 2 dz. Okay, so you'll be having 2 dz. Now this one becomes sine root x, but over here the constant, we will always write it in front. Of course we can write it to the back, okay, but it looks complicated if we write it to the back. And sine root x will become sine, instead of root x you will be having z. Okay, again the constant you can take it outside. So you will be having 2 cos z. Integration of sine, it's minus cos plus c. Original problem was in terms of x. The solution is in terms of z. So we will have to change z again into x by using what we are originally substituting. So this is the final solution. Okay, again, how do we know that we have arrived at a solution? It's when there is no more integral sign. Okay, let me do another problem. Number 3. Okay, so I will do this problem. All right. Okay, I will choose a different problem first. Okay, something that we can relate easily with what I had just explained. Okay, so over here we are having a very complicated looking integral. Okay, we cannot use the basic formula directly over here. So what we will do, we will substitute the most difficult looking term. The most difficult looking term, of course, it is this one. Okay, so let us try to do that. Let x plus log x equal z. Differentiate both sides with respect to x. So if you differentiate this one, you will be getting 1 differentiate of log x will give you 1 by x. So you can easily write this one as x plus 1 upon x, and then dx you can carry it over here. So you'll be having this. And you also notice that x plus 1 upon x, it's actually present over here. X plus 1 by x dx, x plus 1 by x dx, it's also present. Okay, so what we can do, okay, again denoted with I, x plus 1 by x dx will give you dz. And this one has been replaced by z, and then you have a square. So you'll be having this. And if you use the formula, you will be having z cubed by 3 plus c. Z will be x plus log x power 3 upon 3 plus c. Okay, so this is the solution for number 3. Okay, so with this, okay, we have done basic substitution, okay, where we are substituting the difficult looking term. But sometimes we cannot just go ahead with substitution. We have to do something else first. Or in other words, sometimes substitution, it's not clear. Okay, what are we supposed to substitute? Okay, let me illustrate that one with an example as well. Okay, so I will take this one as example number 4. Integral dx Okay, suppose we are having this integral. What exactly are we supposed to substitute? Okay, let me try to substitute something. Okay, some of you may be thinking, okay, this is looking complicated because we are having e power minus x. Okay, so let us try to do that. Okay, e power minus z equal x, z dx, e power minus x will give you dz dx. If you differentiate this one, you will be getting minus e power minus x equal dz dx minus e minus x dx equal dz. Okay, so we are actually getting something that looks like this. Okay, but if you notice, okay, this term is not actually present here. That is e power minus x dx. There is nowhere that you can use this one here. Okay, so if such a case happens, okay, let us know that we have to do something else first with this integral. Of course, we can proceed from here as well, but it will take a few more steps. Okay, so in fact, it is best if we try to write this one in another form. Okay, how exactly do we write it? Okay, that comes with practice only. Only if you practice more problems, then you will be more familiar with the types of integrals and also how do we go ahead with solving them. All right, so let's see. Okay, this one, what we can do, we can take common e power minus x. Okay, so over here you will be getting e power 2x, and over here you will be getting 1. Okay, so this is what we are having. All right, so now what can we do? We can take e power x to the numerator. Okay, e power minus x, take it to the numerator, it becomes e power x. So you'll be having this. Now, what are we supposed to substitute? Okay, again, it's not looking very clear. Okay, some of you may be thinking, okay, we'll substitute the denominator. Okay, but I can assure you that that does not work. Okay, so but just notice this. This one, you can write it as e power x whole thing square plus 1. Okay, e power x whole thing square will give you e power 2x. Okay, so once you had done something like this, you notice that some terms are common, that is e power x. Okay, so let us try to substitute e power x. Okay, once we substitute this one, we will differentiate. You will be having e power x dz dx, and over here you will be getting e power x dx equal dz. So you'll be having this. Now, so with this substitution, what we have achieved? We have achieved a term, okay, that we can easily replace as well, e power x dx. We can easily replace with dz. So if I continue the solution over here, e power x dx will give you dz. And over here, e power x, it will be z. But there is also a square, so z squared plus 1. Now, this one, we can easily use the formula for tan inverse. Tan inverse z plus c. Tan inverse z, but z, it is equal to e power x plus c. So this one will be the final solution. Again, let me repeat that line in case you did not get it. How do we know that we have to proceed in this way? That comes with practice. And also remember that in mathematics, a given problem can be solved in so many different ways. So if you have another way to solve this integral also, it's always good. Okay, so let us now do another problem, okay, where the substitution, it's not so easy. that is, it is not clear what do we have to substitute. Okay, number 5. Root tan x, okay, sine 2x. Okay, again, this one, it's not very clear what do we have to substitute, or at least it is clear, okay, but it's not so easy. Okay, we can immediately think that the most difficult looking term over here is this root tan x. So we can think of substituting tan x. Okay, that is exactly what we will do, but again, we have to do something else first. Okay, so let me try to do that. Okay, what I will do over here is I will still write this one as tan x dx, but I will use the formula for sine 2x. The formula for sine 2x, it is 2 sine x cos x. And then I will still write this line, and also you notice now I will divide and multiply by cos x. So you will be having cos square x, okay, so that, okay, it equates with this one. Why exactly are we writing it like this? Okay, I will tell you the logic for that in a moment. Okay, just let me complete writing it down. Okay, so we will actually be having this one. Okay, in fact, I can write one more line. One more line will give you 1 by cos square x will give you sec square x. Okay, take this cos square x up. Okay, you will be having this. It converts into sec square. So we'll be having this. Why exactly are we doing all this? Okay, so that we can have a term that looks the same. Okay, over here we are having tan x. Okay, everything are different. Okay, but over here, if you notice, we are having tan x. Similarly, over here, tan x. And also remember that if we differentiate tan x, we will be getting sec square x. Okay, so try to bring that one into the picture as well. Okay, so now we only have to do substitution, tan x equals z. We can differentiate both sides. We will be getting sec square x dx equal dz. Okay, differentiate tan, okay, will give you sec square. Okay, so we'll be having this. Now all that is left is using this one over here. Okay, so we will be having sec square x dx will give you dz, sec square x dx will give you dz. We can write that one to the back. Root tan x will give you root z, and 2 tan x will give you 2z. Okay, so from a very difficult looking integral, now it becomes simpler. Okay, the 1 by 2, the constant, I can take it outside, 1 and 2. And over here, this one you can write it as z power 1 by 2 by z dz, 1 by 2. Take the z upwards, we'll be having 1 by 2 minus 1 dz. Okay, so you'll be having 1 by 2 z power minus 1 by 2 dz. So ultimately you will be having 1 by 2. You can use the formula for, okay, we can use this formula plus c. Okay, so this is a bit long, okay, but actually if you get used to it, it won't take you too much time. So z, okay, will give you z power 1 by 2, and over here we'll be getting 1 by 2 plus c. And this one will get cancelled, so we'll be having 1. Okay, so we'll be having root z plus c, but root z, it will be 2 tan x plus c. Okay, so this is the final solution. Of course, I should repeat this line, that how exactly do we know that we have to do, we have to proceed in this way? That comes with practice, because there is no hard and fast rule how to do integrals. Okay, it is only by learning the different types, okay, and learning the techniques correctly, that you will be able to do such problems. Until next time.